Welcome to my channel. This is Franco Pantaleon. In this video, we will learn how to create shear and moment diagram using the area of diagram method for statically determinate beams. Now we have here different formulas showing the relationship between the load, the shear, and moment. So we have here this first formula. This simply means that the change in shear between points A and B equals the area of the loading diagram between points A and B. Now, another relationship that we should take note is this. This equation simply tells us that the slope of our shear is simply equal to the intensity of our loading. Now, we have here another very important formula for determining the change in moment between points A and B. Now, this is interpreted as the change in moment between points A and B equals the area of the shear diagram between points A and B, given by this equation. And another very important relationship is this equation. This equation tells us that the slope of our moment diagram for the infinitesimal point being considered is simply equal to the intensity of our shear. Now, before we will create shear and moment diagram, let's try to take a look for the different illustrative examples for shear and moment diagram. So we have here this first beam. The beam is simply supported with point load at midspan. Now, take note that we have our reactions at the support. So it is very important that prior to creating shear and moment diagram, this tells us that we need to solve for the reactions. Now, another very important thing to consider are the sign conventions. So we have here our sign conventions for solving for reactions. So for this is our sign conventions for solving for reactions. Upward reactions, our sign convention would be positive, and for clockwise moments we have positive. Meaning to say that if we have downward forces, then our sign should be negative, and when we have counterclockwise moments, we will have negative moment. Now, so notice that we start from 0 here. This is our base. Since this is upward, then this must be, the force should be positive. And between these points, there is no change in shear. So the shear must be constant. And until this point load, then there will be an abrupt downward force. And again, we have here an upward force. Now notice, guys, that in this diagram, this is a flat line. So this is 0 degree. And when we draw the moment diagram, if we wanted to determine the change in moment between points A and B, suppose this is A and this is point B, then it is simply equal to the area of our shear diagram. So we have now this, since this is positive, our slope should be positive. And if you notice, if this is 0 degree, then this must be this should be on the first degree. This curve, this line here. Now for a uniformly distributed load, we have our reactions here at the supports, and this acts upward. Then we now have this diagonal line here. And notice that the slope is this. So this is first degree, and your moment should be second degree. So these are our shear diagram, and these are our moment diagram. Shear, moment, shear, and moment diagram. Okay. Now, notice that if your load is 0 degree, then your shear must have plus 1 degree, and your moment diagram again plus 1 degree of your shear diagram. And if we focus on the slope, take note here that if this is 0 degree, then this must be first degree for this particular portion here. Okay? Now, since these have constant intensity shear, then we also have constant slope. That is why this slope is linear. And since this is positive, we will have a positive slope. Now, from this point to this point, since our shear diagram is now negative, then we will now have negative slope, because this area now is negative, below our 0. And again, since this is 0 degree, then this must be first degree. Another, for our uniformly distributed load, 0 degree our loading, first degree for our shear, and second degree for our moment. Now notice, guys, that if we are going to consider the intensity of our shear, take note that the intensity of our shear is decreasing. And since this is positive, our moment should be having slope upward. So this must have a positive slope. Now notice that these have from higher intensity to lower intensity, the slope should be decreasing, upward and decreasing. We cannot have this slope since this is upward and increasing slope. Since the intensity of this is decreasing, then our curve should be upward and with decreasing intensity as defined by this curve here, which is second degree curve. Now, beyond this point, we now have negative shear, and take note that the intensity of our shear is now increasing. And since the intensity of our shear is increasing, then the slope must be, the slope of our moment diagram should be also increasing in intensity and in downward direction. So we have here, it should follow this line. Not this curve, simply because this curve is upward. It should be downward with increasing intensity. Therefore, the slope should be also increasing and going downwards. Now, notice guys that in these diagrams, for these first two beams, the location of our maximum moment is at the point of zero shear. If this is our shear diagram, then the location of our maximum moment is in line with the location of zero shear. Another, for this diagram here, we have zero shear here, and our maximum moment occur exactly where we have zero shear. Now, based on this observation, we can say that the location of our maximum moment usually will occur at point of zero shear. Now, we have here other diagrams for these are simply supported beams, and these are our cantilever beams. Now, notice that most of our computation of our area will fall somewhere for computation of areas for rectangles, triangles, and spandrel. So, therefore, it is a must that we will simplify the basic formulas as well as the location of the centroids for these figures. Okay, so we now have these corresponding area computations as well as the location of our centroids. For the first figure, if we are going to consider this figure here, this is a triangle and this is first degree. The location of our centroid is at x bar equals to b over 3, and the area is 1/2 base times height. Now we have here another figure. This is a second degree curve. The location of our centroid should be b over 4, and the area is equals to 1/3 bh, so on and so forth. Now, based on these presentations, we can now derive these formulas here. Our x bar should be, if this is the degree of our this side here, this curve here, then our centroid should be equal to b over n plus 2. If this is first degree 1, n equals to 1 plus 2 equals to 3. So we have this location of centroid. And for the computation of our area, we have base times height all over n plus 1. If the degree of our this curve here, this line here is first degree, then 1 plus 1 equals to 2. So we have here area equal to 1/2 base times height. And for this spandrel here, if n equals to 2, then 2 plus 2 equals to 4. Again, we can easily determine the location for our centroid. And we have n plus 1, 2 plus 1 equals to 3. Then the area is equal to 1/3 base times height. Okay. Now, in creating shear and moment diagrams for statically determinate beams, the first step that we will do is we will solve for our reactions with sign conventions. Positive when we have upward forces and we have clockwise moment. We have negative sign convention if our force is downward, and we have negative moment when we have counterclockwise moment. Okay, so we have already discussed 4 reactions and sign conventions. Now for guide to drawing diagrams, notice that we have this order. This is of 0 degree, and from the previous presentations, this is of 1st degree, and we have these curves, either this curve or this curve or this curve, if the degree of our curve is greater than or equal to 2 degrees. So these are the common compositions of our shear and moment diagram. And if we have positive shear, then for our moment diagram, we have upward slope. And if we have negative shear, then for our moment diagram, we have negative slope. Okay, and for the area of spandrels, for the computation of the area, we have base times height all over n plus 1. And for our x bar, we have b over n plus 2. So if we know all of these, then creating simple shear and moment diagram using area method for diagrams would be easy. Okay, let us have our first illustrative example. Draw the shear and moment diagram for the following beams. So we have our first beam. This is a simply supported beam with supports at A and B. The span is 8 meters with point load at mid-span, which is 10 kilonewtons. Okay, we will project the sections of our beam. So when we draw our shear and moment diagram, our first step would be to solve for reactions. So this is our shear diagram, and this is our moment diagram. Now what I would like to do is to create shear and moment diagram without less calculations. So this is a 10 kilonewton load, which is at mid-span. Therefore, since this is evenly distributed for either support, therefore our reactions here should be 10 divided by 2. We have 5 kilonewtons going upwards. Likewise, this reaction of 5 kilonewtons going upwards. So when we draw our shear diagram, for shear, we have positive 5. We'll start from the leftmost support A. We have 5. And there are no other forces acting, therefore this must be a horizontal line here. And we have here downward force. This is our load. Minus 5 positive 5 minus 10, which is equal to negative 5. No other forces involved. Therefore, this must be a straight line. Negative 5. And at this point, support B, we have positive 5. So, we now have our shear diagram. Negative 5 to plus positive 5 is 0. Now, the area of our shear, this is 4 meters, and this is 4 meters. This is 5 kN, positive 5, negative 5 kN. The area for this shear diagram, we have 5 times 4, which is equal to 20, positive 20, since this is above 0. And we have 4 times negative 5, which is, the area is negative 20. Okay, we now have drawn our shear diagram. Next thing we would like to do is to draw our moment diagram. Okay, take note guys that the change in moment is simply equal to the change for the area between the different points. So, from this point here, we have 0 moment and plus 20. Since this is the area of the shear diagram is 20. And take note that this is 0 degree. Then, our line should be upwards, which is, this is first degree. So, which is simply equivalent to 20 kilonewton meter. We have, and from this point to this point, 20 minus 20. And since this is negative, then the slope must be downward. So you have 20 minus 20 is 0. So we now have our moment diagram for this point load. Okay, let us create another moment diagram for this uniformly distributed load 10 kilonewton over a span of 8 meters. Okay, let us project portions of our beam. Okay, since this is a uniformly distributed load, it would be easier for us to solve for reactions. Representing with our resultant load, we have 10 times 8, which is 80 kilonewtons, acting at the centroid of our uniformly distributed load. And since this is 80 and acting at the midspan, then our reaction should be even. 80 divided by 2, we have 40 kilonewtons. Of course, we can solve this using summation of moment, but the computations would be lengthy, and we will still arrive at the same result. Okay, for our shear diagram, shear and our moment diagram. So start from 0 going upwards. This must be positive 40. We have positive 40. And this is our loading is 0 degree, then this must be first degree. Okay? And take note, the action of our force is downward. Therefore, we will subtract this total shear force of 80 from over the entire length. So we have positive 40 minus 80 is equal to negative 40 kN. Okay. And this is 8 meters, this must be 4 meters and 4 meters. The area of our diagram here for this particular rectangle is 1/2 40 times 4. So 1/2 40 times 4. So we have the area here should be 1/2 40 times 4. So which is equal to 80. Okay, so the area here should be positive 80. And this area here should be negative 80. So for our moment diagram, this is first degree, then our curve must be second degree. And notice that the intensity of our shear diagram is decreasing. Therefore, our curve should be decreasing. So we must have this curve. The slope of our curve should be decreasing, which is equal to 0 plus 80 is 80. And for this particular portion here, the intensity of our shear is increasing. Therefore, the slope would be downward since this is negative, and the slope should be increasing downward. Okay, yeah, 80 minus 80 is equals to 0. So we have here our (80 kilonewton meter). Take note that the location of our maximum moment is at the points of 0 shear. Now let's have one final illustrative example. Draw the shear and moment diagram for the beam shown below. Locate the point of maximum positive moment. So we now have a simply supported beam with an overhang. Okay, our first procedure would be to solve for the reaction. So we have 10 times 8 plus 4 is 12. So we have 10 times 12. And we can easily solve for the reaction by representing with this total force with this single resultant force, which is 80. Now 10 times 12, which is equal to 120 kilonewton. So, and this is now acting at 6 meter distance from support A. Now, to solve for our reaction B, we will sum moment about point A. We have 6 times 120 divided by 8 in order to solve for our BY. So we have 6 times 120 divided by 8. We should get 90 kN. And since this is 120 minus 90, this must be 30 at support A. The reaction should be 30 kilonewton upward at support A. With reaction solved, we can now create our shear diagram. Okay, so this is our shear diagram. So at point A, we have, starting from 0 upwards, we have positive 30 and positive 30. And if we will consider this span here, this portion here, we have 10 times 8 is equals to 80 kilonewton going downward. So we have 30. Again, notice 0 degree. Our load is 0 degree. And this must be first degree. So we have 30 minus 80 is simply equal to negative 50. So we have negative. This is positive 30. And we will draw this line here. And this must be negative 50. Okay? So we have 30 minus 80 is equals to negative 50. So negative 50 plus 90 is equal to 40. So we have negative 50 plus our reaction at B, which is 90, which is positive 40. We have here 40. And for this portion here, we have 10 times 4 is 40. So we have 40 minus 40 is equal to 0. Okay. So we now have closed our shear force. Now, we would like to locate the point of maximum positive moment. The location of our maximum positive moment is at the point of 0 shear. So we will simply let this variable equal to x. Now, if we are going to see this entire figure here, this figure here, which is negative 50 and this is 30. If we will extend this line here, then we can see that this difference is 50 plus 30 is 80. So we can now use ratio and proportion to determine our unknown location point of zero shear. So you have this span here is 8. Okay, so we can now locate our x. So we have 8 is to 80 using the ratio and proportion, as x is to 30. Now based on this ratio and proportion, we have our x equal to 3 meters. Okay, if this is 3 meters, and then this must be 8 minus 3 is 5 meters. And this is 4 meters. With these dimensions known, we can now easily solve for the areas of our figures, which is our key in determining our moment diagram. Okay, so this triangle, we have 1/2, the area for this triangle is equal to 1/2, 30 times 3 should be positive 45. And 1/2, the area for this triangle, 1/2, 5 times negative 50. This must be negative 125. And the area here, we have 1/2, 40 times 4. The area is positive 80. Okay. So we can now locate the location of our maximum moment. 0 plus 45. 0 plus 45 is 45. And our curve should be this curve, since the intensity of the shear is decreasing. Therefore, the intensity of our slope for moment diagram is also decreasing. This is 45 kilonewton meter. Minus 125. 45 minus 125 is equal to negative 80. And the intensity is increasing, therefore, and since this is negative, we have downward direction and increasing intensity. And this must be negative 80 kilonewton meter. Negative 45 minus 125 is negative 80. Plus 80. So this closest to 0. So this is now our moment diagram. If you like the content of this video, click like, subscribe, and please share. Thank you.